specific, I think now looking more at wake boats, which I think, as everybody has sort of already indicated, is a matter of crucial interest from around the state. It's one of the things that I hear about most is this increased number of larger boats and larger wakes. And the folks at North Lake have begun this incredible study that's going to be really helpful in talking about this issue in the future. So I'm really happy that they are able to be here today. The main presenter is Captain Tim Tyre. He's a professional aviator, an FAA commercial drone pilot. He recently directed the aviation science degree program at Carroll University. Captain Tyre is also the CEO of Terra Vigilis Incorporated, a commercial drone company specializing in critical infrastructure protection and environmental drone survey work. He and his colleagues have been very involved in the North Lake Management District's effort to manage protection of the lake and its shoreline, water quality, and safe boating practices. He co-chairs the North Lake Stewardship Committee, which seeks to educate residents on safe boating practices and study the impact of NLMD guidelines to promote these goals. Captain Tyre has a distinguished record of research with publications in scientific, military, and aviation journals. So before I turn it over to him, I will mention that there are a couple of polls that are now active. You can answer those, give us some idea about who's listening in, and I'll report out on those as necessary. So, but for now, let's turn it over to Captain Tyre.
Thank you very much. Nice job, Tim. And first of all, a big thank you to the Wisconsin Lakes Association for hosting us in this summary of preliminary findings on a study done on North Lake in southeast Wisconsin, the northernmost lake in the chain of lakes, beginning up near just a bit north of Heartland and stretching all the way down to the Rock River in Walworth County.
And before you go on, we're seeing your screen, but we're getting the whole PowerPoint screen, not the slide presentation. So I don't know if there's another, if you want to reshare that. There you go. That looks good.
So this should be a picture of North Lake from the air, looking to the northeast. Is that what you're seeing?
Yep, it's perfect.
Outstanding. So sitting to my left and right are two other members of the Terra Vigilis group and Carroll University. So to my right, your left, is Professor Mike Mortensen, who's a professor of graphic design and now chairs up the aviation science program at that university, which is training students in both fixed wing and unmanned aerial vehicles and all the science that is associated with that kind of training. And to my left, or your right, is Glenn Brandt, who's also with Terra Vigilis. He's our chief operating officer, and Glenn has a strong background in industrial hygiene and spent quite a number of years working with the City of Milwaukee labs as a water quality specialist. So this is a story about, I think, good citizenship. Really three takeaways: good citizenship, the impact of collaborative efforts with scientifically trained groups, university people, public agencies that protect the environment like Sewer Pack, and a lake management district trying to stay ahead of issues and use science to impact public policy formation. And that was one of the reasons that I got directly involved. I thought that was an interesting opportunity to bring science into the mix. So the issue on North Lake began about 5 or 6 years ago with the introduction of a number of wakeboard boats. This is a relatively small lake. It's actually two lakes side by side, a large basin, which is about a mile long, upwards of 70 feet deep, and a smaller lake basin. We refer to it on the lake as the small lake or little lake. The difference in size, the larger one is 330 plus acres. The small one is 108 acres. So 5 or 6 years ago, we had a few wakeboard boats on the lake producing the kind of waves that have been described in Tim Asplin's presentation. and some of the residents were concerned about shoreline impacts and impacts on other recreational use of the lake. As of last summer, we have over 23 wakeboard boats on these two lakes side by side, the majority of which are on the little lake, 100 plus acres. So there was concern, as I stated, among the residents on the lake, and the way that concern was measured was through the North Lake Management District doing a survey. There was a large number of residents who said we need to do something about this, either control them somehow, or control times of use, or come up with some policy to protect the lake. And that was morphed into a series of surveys that were done on the lake, looking at what kind of boats are actually in use, when are they in use, what kind of waves are actually being produced, are they really impactful, and looking for a set of voluntary guidelines to affect the conduct of residents who are boating on the lake. In the meantime, there was, by reason of those surveys, stated interest by residents on the lake to actually study water quality and the impact of these waves. So the North Lake Management District reached to Terra Vigilis, which is a group that we, three of us, represent, commercial drone. Primarily, we do critical infrastructure across the country, protection of nuclear facilities and things like that. But we are very familiar with aerial survey work and now subsurface survey work using drones. So we used drones in combination with traditional measurements of water quality and wave propagation effects on North Lake in a phase 1 preliminary study. That's what I'm going to talk about here quickly. And then we'll continue that study through 2 additional phases, starting again this summer. So let's just move down a touch on the slides. So this gives you a spread of this collaborative effort and the subject matter expertise that went into this initial phase 1 preliminary study. So you can see a number of interested university faculty over at Carroll University got on this project, including Joe Pyatt. Dr. Pyatt is a professor of chemistry and environmental sciences over there. The business analytics people, because this has implications for property value and all kinds of things that you wouldn't think about right away. We had a couple of interns, both in chemistry and environmental science. And then we had some just crackerjack people from the Southeastern Regional Planning Commission, SewerPAC, that helped us with looking at some of the information. And then we had a number of our commercial drone pilots out there flying drone missions, both in the air and under the surface. So we'll continue on now and get right into the meat of the study. This is a satellite view of North Lake. We selected 7 sites to look at for water analysis. Sites 3, 6, 5, and 7 are on the larger lake. 6, 5, and 7 were chosen because those are water inlets to the lake. Site 3 was chosen because that is a reef that extends between the large and small lake that becomes as shallow as 6 to 8 inches and then drops off on both sides. And we'll come back to that. That's an important image to have in your minds. On the small basin lake, we looked at areas where there's an outlet from the lake and where there's fish habitat in a couple of sensitive areas. So those are the study sites where we gathered samples of water and core samples on the bottom to see what was happening with sediments. Next slide. So this is the sort of equipment we were using. This is drone technology equipment. On the bottom left, you see a bottom rover, which was equipped with camera and sensor equipment. There are a couple of quadcopters also in the background here, which were used for aerial activity, and then some sensor probes. And then the next slide will also show you the traditional measurements of water quality used in research of this type, which is the Secchi discs, the tubes for getting core samples, We did use some nest cameras, so we were doing boat counts, and then we had multi-sensor probes that were giving us information on pH and temperature, etc. So, oh, by the way, in the bottom right-hand corner, you see an underwater drone, which was also in use in the study, and you'll see some very compelling videography from that a little bit later. So in the next slide, let me just tell you that we decided to go at 4 domains in this effort to get a sense of what's happening on the lake in the preliminary work. And we started with wave physics themselves. You heard some things from Tim Asplin about waves. We can mimic that in a fairly precise way with these data in domain 1. So we looked at the kind of waves that are actually produced by the common powered vessels in use on North Lake. And those are water ski boats, personal watercraft, pontoon boats, and the wakeboard boats. Both generations of wakeboard boats, those that are used to ski behind and those that are used to surf. Those are different uses of the same kind of a boat. The surfing boat is much more concerned with slow speeds, as Tim made reference to, and a very high bow angle, which produces a fairly substantial downwash, which will have implications for re-deposition of sediments. We also used drones for aerial mapping, which allowed us to get baseline data on 3D imagery for impacts on shoreline. But let's start with just the wave heights themselves. These are busy slides with a lot of numbers. I'm going to go through them quickly, and then we'll show you an easier way to appreciate what this means. So left panel here shows wavelengths on wakeboard boats, heights, and time between crests. The middle shows pontoon boat waves, and the final on the right shows jet ski waves. They're very different waves. They're different sources of energy propagation. In short, what we can tell you from the numbers is that the waves from wakeboard boats are higher. They last a bit longer, and they have some subsurface impacts that are not being seen with pontoon boat waves and jet ski waves. Let's just jump to the next slide. It might be easier to give you a graphic display. So when a wave is measured, we look at wave length, which is the red arrow. So distance from crest to crest. Wave height from the bottom of the trough up to the crest. Wavelengths are often expressed as amplitudes. So if you look at the top graph, you're seeing a higher overall crest. This is aggregated data or average data from many observations, taken about 35 or 40 feet from a shoreline. The straight line across is a calm water index. So if you just look at the 3 different graphs, what you see, if you know about graphical displays of data, is a wakeboard boat which has a higher wave, which has a more substantial subsurface impact, which lasts longer than, for example, the jet ski wave, and then by comparison, the pontoon boat wave. But sometimes numbers and graphs are confusing for people, and so we used a rather unique drone digital imaging system to depict this in a different way. And so we'll move to the next slide now. So what you're going to see here is a graphic display from the air of the difference in these waves. So if you start with the top right, that is waves going over the reef between the 2 lakes from a wakeboard boat. The crests are higher, the distance between is longer, and the energy underneath the wave is also more substantial. So what you'll see if you look close is the development of a plume, which is jumping over that reef and redepositing on the other side. Directly compare that with speedboat waves, which are not as high, don't have as much of a bottom scrubbing effect. And then finally jet skis, which do not have a very high wave at all and no significant bottom impact. So that's a visual way of displaying it from the air. Now let's show you another way to appreciate what these waves are like. And anyone who lives on a lake is going to understand specifically what we're talking about. So in these 4 panels, what we're showing you is what a wave looks like from a bird's eye view at about 200 feet above the ground from a drone, and a fisheye view in the bottom right. So this is a submarine drone on the bottom, watching what happens when a wave moves through. And then on the top right, as if you were a resident sitting in your chair watching the lake, what you see on North Lake, which is peculiar to North Lake, by the way, especially the Little Lake, is a crust or a perimeter, which is only 3 or 4 feet deep, and then it drops off precipitously into deep water. So if you look at the top right of this slide, what you're going to see is these waves that were propagated by a combination of a jet ski and a pontoon boat, very close to one another, deliberately for purposes of this demonstration, to show you the effect of combining the waves. So you can see it rolling through the swim platform, getting into the shallow water. Underneath, if you were a fish, this is what you'd be experiencing or seeing on the bottom, which is not a substantial amount of impact, by the way. And these boats were deliberately put in close. So bottom left, they're very close. They're less than 100 feet from shore. And then finally, top left, if you were standing in the water and you were a 5-year-old and you were just looking about a foot or so above the surface of the water, you would see a wave roll in. And as it rolls in from its propagation source, you don't see a lot of crest. You don't see a lot of crest. Now let's directly compare that. These are all real-time, simultaneous depictions. Let's compare that with what you see with our imagery for a wakeboard boat wave being propagated. Yeah, this is pontoon. So we're going to go to the next one. So this is a wakeboard boat. So same 4 panels, same measurements. There goes the boat. There goes the energy being propagated. And again, as I mentioned, when we looked at the graph, you have energy being displaced above the surface of the water and below. And as Tim Asplin explained, in shallow water areas, this becomes an issue. So here you can see bottom left, the waves are moving in towards the shoreline. The pier you're looking at is bottom left, right underneath the cursor. I draw your attention now to what happens as the wave energy moves across the bottom. So that's the bottom right slide. What you're going to see is our 4-pound underwater drone beginning to be lifted up and down and pounded as that energy moves through. And then if you draw your eye to the top left, you're going to see the wave reemerge and come in on the shore. And if you're sitting in your lawn chair looking, this is what you see. And this goes on for many hours each day, particularly with concentrated periods on weekends. So look close again, top left, and you'll see the bottom being scrubbed and sediments being picked up and pushed around. Very different wave, very different effects. Next slide. So a bit of the technology. When we gathered these data, we used research procedures that allowed us to replicate precisely what we were looking at again and again and again in the same ways, so the measurements are reliable. So that is the flight path of a drone, pre-programmed. It follows that flight plan. So in a grid up and down and back and forth, and it is photographing anywhere from 100 to 300 photographs every several minutes, which are then gathered and stored. And then we take that and stitch them together to get a view of the impact of activity on a shoreline. So the next slide will show you what happens when we take all of those images and put them into a 3D image format. And Professor Mortensen will tell you just a little bit about the specifics of this.
So this 3D model is produced by stitching together a bunch of photos, and you'll often hear the term photogrammetry. And what we're seeing here is the dot coming out, but what we're focused mainly on is the shoreline here, where we've got a lot of polygons that are put together using certain applications. And these are very accurate because we are out surveying the area and using what are called control points, ground control points. So we can get down to an accuracy of even centimeters. And so when we bring it in to the application, over time, we would film these locations once a month. And then over time, we could overlap this wireframe and see if there's any movement in the shoreline, either through maybe receding back. And the advantage of doing this is that we can go out over several years and get a good measurement of what's happening along the shoreline. So that's what you're seeing here with this three-dimensional model.
So our next slide is going to show you another unique application of drones, and that is multispectral imaging. So vegetation has got a infrared light signature, which can be captured. And again, for purposes of comparison over time, we can use this technology to look at the health of plants, both surface and subsurface. And we're going to go back and use these baseline data from our study. We'll go on to the next because we got a lot of material here we want to cover with you. So the second domain we looked at was, okay, once we have all this stirring, what are the impacts on the water itself, the chemistry of the water? So we took water quality measurements of dissolved oxygen, pH, Secchi depths, temperatures, and we took the material back over at Carroll University using their lab for ion chromatography to see actually what the concentrations of significance were in the water itself, in addition to taking organic carbon content core samples to see what's actually in the sediment. And so the next series of slides are going to look at what we looked at with domain 2. And again, we're going to probably go through this pretty quickly because I know they want to have some time for questions, but in each of these panels, what you'll see is the 7 test sites. This is where we were collecting these samples. And there you see a bar graph, which is showing you dissolved oxygen and temperatures across the span of 3 months of study, samples being taken each week. We move to the next slide, we can show you again the water clarity with traditional Secchi depth measurements across time. So much more clear early spring, not so clear by end of summer. Next slide shows pH and temperature across time at the 7 study sites. And then let's move on to the next slide. So we also got a look at what's happening underneath the surface with our drones. And so we took subsurface sampling of plant life throughout the lake and pulled up samples and dried them and archived them for further study. So we can now identify all the species of plants that are active in North Lake. In addition, we looked at the quality of the bottom for comparison purposes from the beginning of the summer to the end of the summer. So let's start with that one. This footage is going to show you what that reef between the 2 lakes looked like at the end of the summer. This is 8 to 12 feet covered with sediment in an area that was, in the beginning of the summer, a fish habitat. The video speaks for itself. There is an impact here. We've got 20 or 30 minutes of aggregated video showing the same thing. We went up and down that reef on the east side, again, 1/4 mile long, 8 to 12 feet, no plant life. And lots and lots and lots of material suspended in the water at the end of the summer. Next slide. So as I said, we also took samples of plant species in the lake, and what we saw were things peculiar to Wisconsin lakes, sago pondweed. We can just move right through these. Eurasian milfoil, Vallisneria. And then finally, we were concerned with, and we sort of found this by serendipity, the boating activity, particularly the boats that are producing deep downwash, are developing plumes, and the plumes migrate with sediment. So we'll show you some video footage which makes it much easier to understand why we're concerned about this. So let's go to the next slide. And again, we'll show a video. Now this is gonna, the drone will swing around. Now we're looking to the northeast. And if you look close in the midline of that slide, what you're going to see as the video continues is the plumes that are being churned up off the bottom migrating toward the shoreline. As they get into the shallow water, they become more pronounced. As they run along that shoreline, they move up to the north and they jump over that reef and redeposit on the other side. So that's the genesis of all the sediment that you saw with the underwater drone footage. A concerning thing. We would defer to the plant biologists and the marine biologists to tell us the ultimate impact of such data. Next slide. So we'll go through some highlights and then we'll have some time for questions. So the preliminary data that we have from the first 3 months of study from last summer, one shows clear differences between the kind of waves that are being generated by different vessels on North Lake. Two, it does show the capacity to produce these sediment-rich plumes, particularly from wave-enhancing vessels on the little lake of the two lakes, probably in part because of the topography of the lake, where it's got that crust that runs all around the outside perimeter. Three, the preliminary data shows sedimentation elements which have potential impact on plant growth, both positive and negative. Four, the preliminary data show great variability in water quality and dissolved oxygen levels in selected portions of the lake. So we took all of our dissolved oxygen measures between surface and 3 feet. We didn't go deep on dissolved oxygen. At the end of our summer, we had a fish die off on North Lake. Cisco, one of the rare fish in Wisconsin lakes, is in North Lake. And at 20 feet or more is where they habitat, and there was a big die off. So when we do our second phase, we're going to look at dissolved oxygens at much deeper levels. Four, the preliminary data showed a good degree of water clarity and dissolved oxygen variability. Five, the preliminary data allowed us to identify selected chemical compounds throughout the waters of North Lake that we're going to study in more detail. And finally, these preliminary data allowed us to get a pretty good survey of the kind of plant species that are active within North Lake. And that gives us a baseline to do some science on what are the potential positive and negative impacts of plant activity in that lake. So we tried to move through this kind of quickly so there'd be an opportunity for questions, and I think I'll stop here.
Great, and thank you so much for that presentation. That's such an interesting study. I think from the questions and from the degree I was able to monitor the chat at all the comments, as I reacted the first time I saw it, the video evidence alone is just is fairly stunning in what it shows. We do have some questions, and I will open this up to both the folks from North Lake and Tim Asplund is still here as well. Let me switch over to gallery view so you can see us all as we talk. The first question that I'd like to ask is, so bladder boaters, if to use the term that the questioner used, I don't know what the exact term for wake boaters or whatever you like, but they tend to argue, we've heard this quite a bit, that wake boat waves are no different than normal wind-driven waves, and that bladder boat waves are really a minuscule percentage of natural waves. Does this study look to show any difference in sediment and shoreline disruption between those two? Did you account for, how did you account for wind waves? And
Okay, so it's two questions that you've asked, and the answer to the first is these data suggest that it's a very different kind of a wave. And I would ask anyone who simply looks at the data, and particularly the videography, both aerially and subsurface, to appreciate that fact, both in the numbers and the graphs and the images themselves. It's a very different kind of wave. It doesn't just go away quickly. They're producing a large amount of energy, which dissipates slowly and becomes an issue as it gets into shallow water. So what appears to be a dissipated wave can reemerge once it scrubs the bottom. Studies in other spots throughout this country and in Canada have indicated that downwash depths as much as 15 to 18 feet are occurring, particularly with wake surf operations, where the boat, as Tim's data showed, is operating at a slow speed, 5 to 8 knots or 9 knots, with a deep stern and a high bow angle. So that's producing a big substantive downwash of energy that can move out from the wave propagating source, the boat, and then scrub the bottom as it gets into shallow water. I would say that it's important to remember there's 2 different generations of wakeboard boats now. One wakeboard boat doesn't produce as much of a down wave, and it's used more for water skiing and trick skiing. That's different from wake surf boats, which operate at a very low speed. They don't plane, they deliberately don't plane, and they maintain that slow speed, high bow angle throughout their operation. That produces a different phenomenon. So these data are not consistent with that claim, and we want to look at it in more depth as a result.
I think this is probably a related question, and it may apply not just, I think the question was asked in the conclusion of Tim Asplin's talk. If 10 feet or less depth are the areas to avoid boat traffic and wakes, what if most of the lake is 10 feet or less? Is the entire lake inappropriate for powerboat traffic? And I might change that a little bit and ask, from the North Lake study so far, do you have a sense, is there a good distance that is how far away these boats need to be for, say, a wake to dissipate? Or is it really a question of the depth of the lake as well?
It's a combination of both things, number one. Number two, we don't have hard science yet to inform us, and that's the reason we're doing a phase 2. And in the phase 2, we're going to look at exactly that question. How far out from shoreline and how deep do the downwashes actually go? And we should be able to answer that with informed science, hard data, ultimately so that policy making and decision making can be informed by the science instead of just people's opinions about something.
That's great. Tim, do you have a comment on that one in terms of just boating in general?
Yeah, I saw that in the question, and I guess the answer is kind of, yeah. I mean, some lakes probably shouldn't, they're too shallow to really have boat activity occur on them without having some impact. That gets into that user area, and how much is too much, and whether who decides if lakes should be no wake or all no wake or not. We have 50-acre minimum right now for no wake restrictions, but I know there are people that would like to see that threshold raised to a higher acreage just because of some of these issues, and we have bigger boats now. Same could be said for depths, but I would say 10 feet is not a cutoff. I use that as above 10 feet. Generally, you're okay, but I'm curious whether this wakeboat study might change that. I'm wondering whether you're seeing impacts greater than 10 feet even in some of these areas and cases. So that was just sort of a rule of thumb. But certainly the shallower the lake, the more likely you're going to have impacts generally. So, yeah, that probably would be maybe ecologically inappropriate.
And then kind of a follow-up question to that, Tim Asplund. At what point does turbidity become a nuisance that might require restrictions? Do we have any standards on that as a state right now? And at what point do we need to start looking at that?
Yeah, that's a really good question. We don't really have total suspended solids or turbidity-based water quality standards like we do for like phosphorus, for example, where there's a clear mechanism. We've got there. I guess there are some concentrations that are on the books, but those are really meant for flowing waters and really highly turbid systems. So these kind of what we're seeing where the lake is otherwise clear and then you see these turbidity events probably wouldn't trigger a standard where you'd have a regulatory trigger at this point, unfortunately. But, again, that's where data collection and showing, some of the, if you can do a cause and effect, we are moving ahead with things based on aquatic plants. So if you can demonstrate the aquatic plant community has somehow been impacted or impaired and that the cause is turbidity or some of the things like the video has evidence that Captain Tyre showed, that, that could be part of the contributing to make a case that there is an impairment and that the solution might be to do something about it.
Great. And with that, I think we're out of time. I invite everyone to jump over to the plenary session right now. Join Tim Asplin's boss, DNR Secretary Preston Cole, former Governor Tommy Thompson, and Marissa Jablonski talking about the Great Waters Initiative in Wisconsin. So thank you to all of our presenters here and for everyone listening and the great questions. This is a conversation that we'll continue to have throughout beyond the end of Wisconsin Water Week without question. So thanks to you all.
Thank you.
Thank you.
Thank you.
That was great. Thank you so much to all.